So it's a continuation of your AS organic chemistry. So the first part of organic chemistry in A2 is related to benzene, and benzene is something that's very similar to alkenes. What happens in an sp2 hybridized carbon atom? That is that whenever carbon forms a double bond, it's sp2 hybridized. 3 of its electrons, they get pulled in 3 different directions. It's usually attached to just 3 atoms, whereas the 4th electron of carbon is in a p orbital. It just remains in a p orbital. So you've got 3 sp2 hybrid orbitals, while the 4th one is just a p orbital. So 4 electrons, one here, one here, one here, and the 4th electron is not doing anything initially. So carbon makes 3 bonds. 1 electron bonds here, 1 electron bonds here, 1 electron bonds here. And the 4th electron that is initially unused, it eventually ends up overlapping with the neighboring carbon atom's 4th electron, and they end up forming pi bonds. So the carbon has, this one is also sp2 hybridized, 3 electrons bonding, and the 4th electron not doing anything. So they start overlapping with each other and they end up forming a pi bond. And for an alkene, the electron density of a pi bond, the middle part has a very high electron density because the electrons are very localized in a very small space. And then we started talking about benzene. In benzene, you had a similar structure. This is what benzene looks like. It's C6H6. Carbon is forming 3 alternating double bonds in a hexagonal ring-like structure. So it's like similar to alkenes, but it's slightly different. What happens is that the double bonds, they kind of get mixed up, and instead you get a delocalized electron cloud. So this is the skeletal formula of what benzene looks like. And this is the detailed structure like this one. Let's focus on this one. So carbon is still sp2 hybridized. Like if you focus on this carbon atom, it's making 3 normal bonds, and the 4th electron is not doing anything. This carbon atom, it's making 3 normal bonds, sigma bonds, with 3 atoms on either side in a fan-shaped manner, and the 4th electron is not doing anything. So each carbon atom is sp2. This one also 3 bonds, while the 4th electron is not doing anything. What eventually ends up happening is that the 4th p orbital that is not doing anything, that they start overlapping, and all of them, they kind of get mixed up. And as a result, you get a pi electron cloud on top and below on the underside of this structure as well. So you get this huge pi electron cloud, which is kind of similar to what happened here. So this is kind of similar to what happened here, but in an alkene, the pi bond is like, it's very localized. It's present at a very specific place. But in a benzene molecule, the pi bond is everywhere. Because the p orbital over here not only overlaps with the carbon that's on the left side, but at the same time, it's also overlapping with the carbon that's on the right side. So the pi bond, so partially it's forming a pi bond over here, and partially it's forming a pi bond on the right side as well. And that applies to every one of them. So the electrons are kind of more distributed. The electrons are not only overlapping over here, but they're also overlapping on the right side. So as a result, one major difference between an alkene, where the pi electron cloud has a very specific place, and one major difference between benzene is, in benzene, the pi electron cloud density is more distributed, and it's got a lower charge density compared to alkenes. So this is something that we did, that this pi electron cloud, this ring-like structure, so which is why in benzene, the double bonds are not, you don't call them double bonds. Instead, the double bonds kind of get mixed up. So instead, you show them with a ring-like structure. Although this one gives you a pretty good idea of what benzene looks like, but always think of the double bonds as not being in one place. Think of them as delocalized electron clouds, where the orbitals are all overlapping with each other. So that is what benzene looks like, and the electron density is lesser. Zaid, पिछली क्लास अटेंड की थी?
No, sir.
चलो मैं फिर से थोड़ा सा वो क्विकली एक्सप्लेन करो. ये समझ आया कुछ?
Yes, sir.
So, Iman, is this, did you get this part?
Yes, sir.
Achha, so So remember alkenes, that's what you did in your AS, and that's benzene. The only difference is this p orbital over here overlaps on the left side, but it also overlaps on the right side. So the electron is very distributed and the electron density is lesser. So that's the only difference between the two, alkenes and benzene. High electron density, low electron density, that's the major difference. And because of that difference, the reactions kind of get, benzenes have slightly different reactions compared to alkenes. So we did the mechanism for alkenes. Now in alkenes, you had electrophilic addition of alkenes, which you did in AS. The electron density was very high. So this was the bromination reaction, where you had a bromine molecule, and the bromine molecule would get polarized because the electrons in the bromine bond, there was a very high negative charge over here because of the double bond, the pi electron cloud. So the electrons in bromine would get repelled. They would be pushed away, which is why this bromine will have a slight negative charge and the bromine on the other side will have a slight positive charge because it's going to get polarized. The positive bromine is going to be even strongly attracted to the electrons, while the negative bromine is going to get further repelled. The positive bromine is going to pull all the pi electron cloud and it's going to bond with it. So this bromine over here, this positive bromine over here, that one, just a second. So the positive bromine over here, one second. So the positive bromine over here got attracted to the electrons in the double bond. They all got pulled over here. And when these electrons, they get pulled by the positive bromine, the carbon over here became a carbocation. And in the next step, the Br minus one that had broken off would then come and attach with that. So that was what was happening over here. Now, so this is all alkenes reactions. Now, the last time, the same reaction we repeated with benzene. And this is what we did last time. This was the first benzene reaction that we studied, which was bromination. But the name of the reaction is different. It's called electrophilic substitution. Now, in electrophilic substitution, you had, remember, the electron density is lesser. So what we talked about was that when we were talking about this one was that the bromine molecule is going to come in. And this is what was happening. Let me keep this away at the moment. So what happened was, forget the FeBr3 at the moment. Forget this as well. So the first thing that would happen is that the bromine molecule, because of the electrons, lots of electrons over here, the electrons over here would be repelled. So this electron over here will get pushed further away. But the repulsion would not be that strong because remember, the benzene pi electron cloud polarizes bromine, but the polarization is lesser compared to alkenes. So it's going to polarize this molecule, but not to that extent. So the polarization is going to be very weak. The electron, the negative charge over here is going to be kind of tiny. It's going to be small. And the positive charge over here is also going to be, it's also going to be smaller. The polarization would be very weak. The electron would only slightly get pushed because the negative charge density is not very, very high. So that's one thing. Zahib, is this clear? Is this clear or no? Sam, is this clear? Minhail? Hafsa?
Yes, sir.
Acha, just a second. Acha, so one second. Acha, so this one.
Right, so, like in conclusion, the benzene will only polarize the bromine molecule just a little so that it would have partial charges.
Yeah, but the polarization is not going to be very high. Okay, that was one important, because this is where A2 organic chemistry starts. Okay, so that's why I'm spending a bit of time on this. Remember this one. Compare it to alkenes. Okay, this is your old AS. Compared to alkenes. In alkenes, polarization it's got a high charge density. This double bond over here, because the electrons are more localized. They are all concentrated at a very specific point. So they push the electrons very strongly. And the positive bromine gets attracted to the electrons very strongly, and the negative bromine gets pushed away very, very strongly. So there's going to be high polarizing over here. And the reaction doesn't need any help because it happens at room temperature. Bromination happens at RTP. But over here, the problem is, ये जो benzene में मसला ना, that is, if you have a benzene, so what's going on is that the electrons are not really getting pushed. Like the polarization is not happening, or it's happening to a very, very small extent. Is clear? बात समझ आइए?
Yes, sir.
Achha, so that means if the polarization is not really happening, the positive bromine is not going to be attracted to, this thing. So the attraction is going to be very weak. The electrons, it's not going to be attracted to the electrons. That means you're not really going to have a reaction, because the positive bromine, very weak attraction. So there's almost no attraction at the moment, right? So in case of benzene, bromination doesn't really happen at RTP. It doesn't happen. It needs help. And that help is provided. Ye baat clear? Is this clear? Right?
Yes, sir.
So the reaction needs help. Like you need to somehow increase this positive charge so that it becomes interested in these electrons. And that's where the FeBr3 catalyst comes in. This FeBr3 catalyst, what it does is, iron is a catalyst, and in transition metals, you should know that iron has it's got a large number of protons. Transition metals usually have very high attraction for electrons, which is why they're very unreactive. They don't lose electrons. Like gold has a very strong attraction for electrons. Iron also is kind of unreactive, doesn't really lose electrons. It's got an attraction for electrons, which is why they're good catalysts. So iron, what it will do is it will start pulling the electrons from the other side. So benzene over here is, so think of this in this way, that benzene over here is trying to push these electrons in this bond towards the right, pushing it away, repelling it. And iron on the other side is trying to attract those electrons, the very same electrons. So the very same electrons are getting attracted. Now the polarization would increase. The electrons will move more towards the right. And the negative charge on this bromine will increase, and the positive charge on this bromine would also increase. Is that idea clear? That the polarization is now increasing because of this catalyst that's added. Is this clear? Zaib, clear?
Yes,
Yes,
sir.
sir.
Achha, ab ye hoga ki now the bromine has a very strong positive charge. Now it's really interested in those electrons. Now it's really interested in those electrons, and the molecule is going to get polarized and it will split up. The negative bromine will get attracted to the iron, and the positive bromine will get attracted to these electrons over here. And that's the next step. This is the whole mechanism of electrophilic substitution. The reason we call it electrophilic is that any molecule that gets attracted to electrons, that's an electrophile. You've studied that in AS. Anything that's attracted to electrons, that's an electrophile. So bromine is acting as an electrophile. So that's the next step. So your positive bromine, this one, it gets attracted to this electron. Isko main highlight kar leta hu. It gets attracted to this p orbital over here. Let me shade it in. Achha, so this orange p orbital over here, it gets attracted to that orange. It becomes interested in that electron and tries to pull it towards itself, eventually bonding with that. So that orange p orbital, that's gone now. Who took it? It's the bromine, the positive bromine, that came and took that electron and bonded with that. So is this clear?
Can I ask a question?
Yes. Yes, you can ask the question. Iman?
Okay, as far as I know, the orbital, actually, benzene has got delocalized electrons, right?
Yeah.
Can you hear me?
Yes, I can hear you.
Benzene has got delocalized electrons. So why is it not reacting directly with bromine positive? The delocalized electron should.
Your voice is breaking up. Iman, can you type the question?
Sure, I'll type.
Iman, can you say that again?
I'm just typing it.
Yeah, I can hear you now, actually.
I was saying that benzene is highly stable, right? And it has got 6 delocalized electrons. So
Yes.
why it cannot directly react with bromine positive and pull it towards itself?
No, because previously bromine wasn't getting polarized. So the positive charge on the bromine was like really small. Like if it's really small, why would the electrons get attracted to that bromine? They're not going to get attracted to it, right?
Oh, okay.
Like bromine needs to be polarized. Like this bromine has to, it needs to have a positive charge. I mean, bromine on its own is a non-polar molecule, right? Because the electrons are right in the middle. So it's a non-polar molecule. So benzene has a very low charge density. It's not able to push these electrons to the right. Like if the bromine molecule comes in, the electrons that are in the middle, they need to be pushed, they need to be repelled to the right, right? That's why this bromine will get a negative charge and this bromine will get a positive charge, right? Is that point clear?
Yes.
But the benzene isn't able to do that because the electron density is very, very less, because the electrons are very distributed. Is that clear?
Yes.
So you need the iron on the other side. So there's this benzene that is pushing these electrons to the right, and there's this iron that's pulling the electrons to the right. So it needs help in polarizing the molecule. So when these electrons, they get pushed to the right because of the attraction towards iron, and also because of the repulsion from behind, that's coming from the benzene, then the bromine molecule gets polarized, and this bromine gets a large positive charge because now the electrons in the middle are now all pushed to the right. And usko main show kar deta hu ki they're getting pushed to the right now, right? Is that clear?
Yes.
So now the molecule is polarized, and now this bromine is going to be interested in those electrons over here. Okay? Because now it's got a big positive charge. Is that clear?
Yes.
So, and remember, most of benzene's reactions are going to be electrophilic substitution reactions. The ones that we study even further on, that most of them would be electrophilic. I mean, electrophilic substitution is a big thing in A2 chemistry, so that's why we're spending more time on this. Now, so make sure everything is clear about this. So this bromine is now interested in this. It's going to pick one of the p orbitals, right? It's going to be interested in that. So it takes electrons from the p orbital and bonds with it. I mean, the other Br goes and forms a dative bond with iron. Like it takes the electrons, iron pulls those electrons further to it and ends up forming this FeBr4-1 ion. And there's a dative bond formed, which is kind of a weak because iron has this attraction. The reason iron is a good catalyst is that iron has an attraction for electrons, but it's got this weak attraction for electrons. Not that strong. Because you don't want iron to strongly attract that. You don't want the catalyst to permanently bond with this because you want the FeBr3 to be recovered again. So iron, we all know it's a metal. It doesn't really gain electrons. So the attraction for iron for these electrons is only very weak. So it's a very weak dative bond that's going to break eventually at the end. So we're going to discuss that at the end. Now coming back to this, you've got Br, and it has taken those electrons. So the benzene electron cloud over here is now missing an electron because previously there were 6 electrons that were delocalized, 6 p orbitals. But now you've got only 5 because one of them has been taken up by a bromine over there. And that's gone. So one of them is gone. And the benzene ring will now have a positive charge because it's got 1 electron missing now. So it's going to have a positive charge and it needs that electron back. And hydrogen over here, it's very electropositive. Hydrogen always wants to lose electrons. So what will happen is that once the benzene electron, so once the benzene electron, just a second. Just hold on 1 second. This is coming back to this. So benzene lost an electron, got a positive charge, and it needs the electron back again because there's an electron deficiency now. Somebody took its electron. So hydrogen over here is willing to lose electrons. Hydrogen, if you know, it always forms H+1 ions. So it's a very electropositive element. So hydrogen is lost. Hydrogen gives its electrons back, and the p orbital over here, this one, is reformed. So this orange one, let me mark that in orange. So this one over here, where did it come from? Because hydrogen gave those electrons back, and the p orbital came back, and the delocalized electron cloud, and there's no longer going to be a positive charge. So that remove that positive charge in the middle, because the benzene electron cloud is now complete again. But as a result, an H+1 was lost, and that H+1 went to the negative ion, and what it did was that it attracted the Br and ended up forming HBr. Okay, so is the mechanism clear? This one?
Yes, sir.
Okay. So Iman, is this clear? Or बाकियों clear है?
Yes.
Okay. So remember, this is important, and and obviously this is just a 3-dimensional representation. Yes.
This FeBr ion that has formed in the second step, that isn't a complex ion, is it? Because we need
It is kind of a complex sign. Okay. The dative bonds are kind of complex signs. This is a complex sign, which is why we're writing it in square brackets.
But aren't we have only Br that is forming a dative bond. So we have only one dative bond. So how is it a complex sign?
Even if it's one dative bond, it's still a complex sign. Like the complex sign mein ye nahi hota ki usne, it's going to make lots of dative bonds, right? Like even if
I thought all the bonds are supposed to be dative. If like only one bond is dative, that can be a complex sign.
That can be a complex sign, but the ones that we study, we're just going to study a few complex signs, okay? So you don't have to go into that much detail about complex signs. Okay, the only thing you should know is that Fe, a transition metal, is always interested in electrons. It's got a lot of protons, like 26 protons, which is why it doesn't like to lose electrons, and it has this weak attraction for electrons. So the bromine electrons will be pulled towards iron just very slightly, not very strongly. Because if it pulls the electrons very strongly, then the bond is permanent. फिर वो वापस नहीं देगा. The bromine will be stuck with iron forever. यहाँ पे what happens is the catalyst is regenerated. The H+1 breaks off, goes over here, gets attracted to the negative ion, pulls the electron and bonds with Br, and the FeBr3 is regenerated. But anyways, the whole summary is bromine molecule is not polarized enough, so you need a catalyst which pulls the electron from the other side. It gets polarized. The positive bromine gets interested in this electron over here, and as a result, it bonds with it. The benzene electron cloud becomes partial. It needs the electron back, pulls electrons away from H. The H is lost. the benzene electron cloud becomes complete again, and the H is lost, that forms HBr. So I'm going to draw the mechanism now that you're going to write in your, and this is the one that's going to come every time pretty much. So this is the mechanism that you're going to draw in your exams. I mean, obviously you're not going to draw the three-dimensional drawings over here. So this is the exam mechanism, which is going to be the same thing except a simplified version of that. So it's going to be, the benzene would usually be represented by its skeletal formula most of the time. So that's benzene's skeletal formula. Here's your bromine molecule with its 2 electrons in the middle, and that's your FeBr3.
So is this the same electrophilic substitution?
हाँ मतलब same mechanism, मैं दोनों साथ साथ रख लेता हूँ, ठीक है? ये मतलब exam के अंदर you're going to draw this one, right? So you're going to show this arrow, then this arrow goes over here. The electron gets pushed over here, and the electron is getting attracted by iron from the other side. So that's the first step. Second step is, I mean, what's the second step? The carbocation is formed. So you draw the carbocation, that's your second step. So take the same benzene, and now the ring in the benzene would be partial. It's going to be on 5 of the carbons, but not on the 6th one. It will have a positive charge. Just a second. Let me correct that. This one. So you're going to have this positive charge. Show the H and the Br now, because now look at the left. It's got an H, but it's also got a Br now. So you have H and the Br, and in the next step, you're going to show the electrons from H leaving the H and joining the benzene electron cloud. That's what's going to happen. And on the other side, you'll have FeBr4 or FeBr3 minus 1. Sorry, FeBr4. So that would be next to it. And that will have, so that one will have a minus one charge. And the last step would be, I mean, the last step is the products. The products are going to be formed. So that's your very last step. So just copy the same. So the H is gone, leaving only Br there. And what else is formed? HBr is formed. And the next thing that's formed is FeBr3 is formed back again. So you'll have your FeBr3 back again. Or isko main, let me put arrows. So remember 2 steps.
Sir, in the first step, aren't we supposed to show the partial positive and partial negative charges of the Br?
Sorry, wo main dekh raha hu, wo bhul gaya. So this is partial positive and that one is partial Let me just quickly check where else is that missing. That's about it. This one, you should show a positive charge over here, this one. And the rest is kind of fine. Okay, that's fine. So that's your exam mechanism, and they're going to ask you frequently to draw that, very frequently. So that's something that's really, really important. Okay, so I'm going to put that in this box. Okay, is this clear? Because remember, everything that we're going to do now from now on is going to be related to electrophilic substitution. All clear?
Yes, sir.
Yes, sir.
So let me just write the conditions for that. Remember electrophilic substitution. So let me just write the whole summary. Like, we just do the mechanism. The summary of the reaction is that you add like without the mechanism. So I'm just writing the reaction without the mechanism, just the equation. So it's going to be just copy the benzene. So one thing is, you should be very good with drawing benzene, because so that is going to be asked over and over again. So the summary is, here's your benzene, and what are the conditions? There are two conditions. This can happen with the Br2, and you can have FeBr3 as a catalyst. Or there's another one, which is you can also have AlBr3 as a catalyst as well. So don't get confused if they write AlBr3, because that's also a catalyst. So Br2, and what will happen is substitution will happen. This thing will form like one of the hydrogens. Remember, in the skeletal formula, they don't show the hydrogens, but remember, there are 6 hydrogens that are surrounding it. So here's your Br, and an HBr would be produced. So this is the reaction without the whole mechanism. So that's just your equation. Balki Br2 go, I'll just write next to it. And it will happen with another halogen as well, and that is chlorine. So kind of the same reaction, everything kind of the same. And this one will happen with chlorine as well. So the other reaction, let me just copy the same one. And the other one is this. I'm just going to change Br2 to Cl2. Everything remains the same. Except that the catalyst also changes, because if instead of FeBr3, it's going to be FeCl3. And instead of AlBr3, because you don't want Br to interfere, so instead of AlBr3, you're going to have AlCl3. And instead of Br getting substituted, you're going to get Cl that is getting substituted onto the benzene ring. So instead of benzene having 6 hydrogens, it now has a halogen attached to it. Okay, is this clear? The whole thing. That's the summary of the first reaction.
Yes.
Yes.
Yes, sir.
Jaldi sir, let's do the second one. The second one is also electrophilic substitution. And basically, from now on, it's going to be the same thing. Okay, so I'm not going to repeat this. It's going to be the same thing. The same thing would happen, but with the different substance now. Now, this one is called nitration of benzene. Now, nitration of benzene. Nitration is when you have the electrophile is going to be, like in the previous case, it was Cl2 or it was Br2, but now the electrophile is going to be NO2 plus. और इसके साथ भी वही मसला है कि you need to polarize it first. Like like you had to, I mean, the problem was the bromine wasn't really interested on its own. You had to polarize it first. So the same thing happens over here as well. The first step is step 1. You would have to completely polarize it. You would have to create this electrophile. So step 1 is like no reaction would happen unless you have this electrophile. So concentrated sulfuric acid, let me write the whole summary of the reaction before we do the mechanism. So the summary of the reaction is, as a summary is, you got a benzene. With the ring. And the conditions for this reaction are that you add concentrated sulfuric acid and concentrated nitric acid. And the temperature is going to be 50 to 60. And as a result of this, an NO2 will get attached. In the case where bromine was getting attached, now it's going to be the same thing. The mechanism would also be similar. We're going to talk about the mechanism. But now in NO2, that's the electrophile that's going to get attached to it. And this is going to be called a nitrobenzene. So instead of having 6 hydrogens around it, it's going to have an NO2 that's going to be next to it. Or the mechanism is kind of the same, slightly different because very slightly different, but otherwise everything would be kind of the same. So we're going to talk about the mechanism of this reaction, which is also electrophilic substitution. So that's also the same one. But obviously you have different things and some stuff would be different. So we'll talk about that tomorrow now, okay? And we'll talk about the other electrophilic substitutions as well. So let's continue tomorrow now.
Sir, can you send me the past recording as well?
ठीक है, मैं दोनों शेयर करता हूँ, ठीक है?
Sir, thank you, sir.
चलो ठीक.
Yes.
Okay, sir. Thank you.
Okay, take
Allah
care.
Hafiz.
Hafiz.